The goal with the discussion is that let's see if in half an hour we could all be on the same page with respect to understanding how Jupyter and its role in building predictive model is important, how it could help in adding the aspect of human in the loop, which we see a lot of people talking about these days. Paco yesterday talked about it with respect to online learning using Jupyter. So let's see if we can dig a little bit deeper into it and understand what's going on. So before we get into the details of the topic, we all like building models, right? It's fun. Machine learning is the buzzword these days, and we all like building, solving difficult problems, interesting problems. So the fun the fun turns to misery when we actually have to have a lot of control on these models. So it's fun to play on a toy data, but more often than not, when we apply the same examples that we see online to a real world data set, we find the hell just breaking loose, and the model just goes out of control and it doesn't give the prediction that we want. And so I use this as an example. So more often than not, when we plan a vacation, we try to check, what's the forecast for the weather. And how often it says that it's sunny, and then maybe it starts raining, and it's going to say it's rain, but it never rains. So this is a typical use case where this person has entered an incorrect zip code, and he got some prediction from the model, and based on which the person may plan her vacation. But the important question is, the prediction actually went wrong, and whose fault is it? Is it the human's fault? Should the model have detected that it was an incorrect zip code that was entered? So whose fault is it? But at the end of the day, it's the human who has suffered here, because this predictive model was applied to a real world problem. So with that, again, I'm Pramit Choudhary. I'm a lead data scientist at datascience.com. Of late, I've been exploring better ways to evaluate and understand and explain the model and decision boundaries. And today's talk is around how we can understand the decisions that the model is learning on, and with the help of Jupyter's interactiveness. So that's the agenda. So we're going to start with defining first what we mean by model interpretation. Make sure we are all on the same page. Understand what do we mean by when we say the dichotomy between performance and interpretation. Introduce Cater. We're going to also do a small walkthrough on the analytical workflow and how datascience.com platform is helping solving that problem. A quick demo and then a Q&A. So let's get started. So defining interpretation. As per the literature, the definition of interpretation as such is still ambiguous. To many people, it may mean different things. Typically, when we solve a predictive modeling problem, data exploration is the first important thing that we have to do, right? So Jupyter, again, helps in that, because it's very easy to get started on the choice of the kernel, and then you can load the data and then start exploring. So in this example, what I'm showing is the use of TensorFlow and doing component analysis on that. So this is the MINS data set, and here I'm just trying to see that with 3 components, how well can I cluster the digits together, which are of the same type. So in this example is 6, which are all clustered together. There are some errors here, but we get an idea of what we want to do with data exploration. For some, it may overlap with model evaluation. So we know when we build a predictive model, there is some objective function that we try to optimize on. A cost function, some may say. At the end of the day, we look at an accuracy, and we say, oh, we got 90% accuracy, we are good, or we got a 90% F1 score, we're good. In this case, what I'm showing here is on a multi-label classification example. Is the plot on 3 classes and showing you the area under the curve with the help of ROC. So this is another aspect of model evaluation. But the important question is this enough? So far we saw data exploration, we saw the aspect of model evaluation. Now the question is this enough? And with that, let's define model interpretation today. So model interpretation is about understanding machine learning and statistical modeling behavior. With model interpretation, the three most important questions that we want to answer is, why did a model behave in a certain way? What are the relevant variables driving the model's outcome? What other information can a model provide to avoid prediction errors? So can it help us in understanding the feature interactions that are happening? And we'll see how it gets complicated in the next couple of slides. Can we trust these black box models? So now, since these predictive models are finding their way into real-life application, from driving cars to predicting human behavior to predicting medicines, so it's just everywhere. And then the important thing is, can we blindly trust this black box model? Is there a way for us to unblack box it and see what's going on within it? So as we solve these modeling problems, more often than not, we try to balance between model complexity and error. How many of you guys here have an understanding of bias and variance? Can you see some show of hands? Perfect. So, more often than not, we want to be in the middle, which is the optimum point, but in reality, we are here. So as the bias decreases, as we start overfitting or overtraining, we find that we are getting bias to the patterns which the model has understand, because these models are trained on a static data set. And as we train more and more, we start overfitting the model and then getting too biased to the patterns which the model has already understood. And then when we try to evaluate it on a test data set, we see, oh, I'm not doing as good as I thought, so my 90% accuracy has gone for a toss now. This is another example. This is about understanding the optimism, right? So as I was saying, over a period of time, we feel that, oh, maybe if we add more sample data set to the training set, I might start decreasing the bias over a period of time, and then we have to keep controlling the test error which is going up. And in this example, it's a good example between wealth and happiness. So initially, the model thinks that, okay, maybe if I could just learn a linear model, I'm doing somewhat okay. Now, if I try to be very precise, then as you can see on the right-hand side, the model has completely overfit. And when we see that, is the increase in wealth actually driving more happiness? Now, it's a question that we as humans may agree or disagree on. And that is another important question that we're going to be discussing today, that even though when we say human in the loop, we as humans often disagree too. So then how do we make a machine understand what exactly we want as results? So that's the point with respect to why do we need model interpretation. So model interpretation helps in exploring and discovering the latent or hidden feature interaction, and that's the most crucial aspect of any predictive model. If one has a good domain knowledge, if one has a good understanding of the feature interaction, building models could become much easier, right? But in real life, what happens is that we as humans often find in solving a use case which we may or may not have the complete domain knowledge about. I'll give you a good example. So I was doing predictive modeling for to avoid preventive failures in oil and gas industry. And then after some time, I was doing matchmaking with using predictive models. It's a totally different ballgame with no domain knowledge. Now, if I have to build a model, I like the domain. So it's very difficult for another person to trust me if I say that I've built the best model. So how do I convince my boss? How do I convince my other audience that what I'm learning is exactly what is being is what we could actually relate to as humans? Then the other aspect is with respect to understanding model variability. So as we were mentioning, this when we train on the static data set, and if we are applying it to a real world problem, which means that we are deploying the model. Now, the real data set which is coming in, it may or may not be, the feature space may or may not be bounded by the same range that we have trained on. So now this variability that is there, that could change over a period of time. And how do we control that? It could be that, oh, maybe we go about and retrain the model as soon as possible. That may be expensive. Even so, we want to understand what feature actually got changed in the environment so that I could capture it while I'm retraining. It helps in model comparison. So these days, there's a concept called champion model, buckets of model, gem of model, and whatnot, where we there are systems where you could just dump a dictionary of models and it will give you the best model that it has learned on. Even when we have to do that, there is an often need to understand why did my random forest give me an accuracy of 90%, whereas my linear regression is giving me 95. I'm just making that up. I don't know if that's true, but I'll not be surprised. And then there is a need to understand, again, how did my features behave? What is that random forest learned on that my linear model didn't, or vice versa? And then going back to the last point again, we as data scientists, it's very important to build domain knowledge. And the sooner we do that, the better we'll be able to build models. Most important thing, transparency in decision making. Right? So it's getting applied to real world problems. So we need transparency and ways to understand and articulate, communicate what exactly did the model train on. It's become very more important in regularized industries like healthcare, finance. This is with respect to the credit reporting, US government's mandate on credit reporting, so that when these credit reporting systems are making predictions, they're required that when they articulate why did a model make a certain decision, they are able to convey that it was not biased maybe on sex, religion, income, or education. If it was, then give the right to person to maybe change it or to challenge that decision. So far what we have discussed is we defined briefly model interpretation, which is at the core understanding how these models are behaving. We also talked about why with respect to model transparency, helping in model comparison, and helping us make better decisions. But the important question is all this is good, but in reality, are all predictive models interpretable? That's first thing. And do all interpretable models predict well? So these are like real world challenges. So this example is we all know about the Netflix prize competition that happened a couple of years back, right? So in 2008. So Bell and his group, they were able to, I think, create the best model possible, but they reached a point where they could, I think from the paper, it seems that they tried all possible combination of the features that they could think of. And their decision was that they can't do anything else other than increasing the sophistication of the model, which is adding to the complexity. Now that's another problem. So at times we run out of options as to what, depending on the feature set that we have, that we can interact or make them interact so to get the best decision. And then there are certain other causal effects that humans can't think of, and it's up to the model as it learns the different data that it could determine that. And which means that maybe we have to move to more sophisticated models like gradient boosted random trees or SGBoost, or some form of neural network that we could think of. So here's an example that I have for you guys. So we have two variables here. Let's imagine that the ones which are in red are people for whom the credit card needs to be denied, and the green are the people for whom the credit card reporting system needs to approve that card. So now, if we have to fit a model on this, we can draw a simple build a simple linear model. And this is somewhat okay. We might get an accuracy of 80% or so, but we have some green ones here, which are falling into the bucket of the credit card getting denied. And then we have some red ones here, which should have, for whom the credit card is getting approved. Can we do better? Yes. Right? We can overfit it. Now, if we have created a complex decision boundary. But in doing so, when we first created a linear model, so we could all relate to linear models, right? Because linear models are y is equal to ax plus bx, and y is equal to ax1 plus bx2. So this A and B's are coefficient, and we know that these are linearly dependent to the change in Y. So we know a unit change in the coefficient would add to a unit change in the actual prediction. We all are very happy because we have total control on it. But as we saw, we made errors. We created a complex decision boundary. Now we have lost that privilege, and we have added to our complexity. Let's take it a step further. This is a non-monotonic increasing function. So linear models are increasing, monotonically increasing functions. So with monotonically increasing functions, it's easier to correlate with the coefficient or changing coefficients. These complex decision boundaries are non-monotonic, which means it's not completely increasing and it's not completely decreasing. There's like a lot of waves and spikes and in between. How about if we had concentric circles? The blue ones are the people for whom the card needs to be approved, and red ones are for whom the card needs to be denied. We can't do much with the linear model now, do we? So this decision boundary that we have learned here is using a very simple neural network with some 100 hidden layers, and it seems to be doing good, as you can see here. So let's see if we are on the same page with the problem here, right? So what is happening is, and let's redefine the problem as well. So the data scientists are choosing easy to interpret models like simple linear models or decision tree over high performing neural networks or ensembles because they want to be in control, but in doing so they are sacrificing on accuracy for interpretability. This is very common in finance industries as well, and healthcare. Other problem is the community is struggling to keep pace with the new algorithms and frameworks which are coming out. We have H2O, we have sklearn, R packages, and many others. But what if there is an interpretation library that's model agnostic, is human interpretable, framework agnostic, could work across multiple different frameworks, language agnostic, R, Python, Scala, allows one to interpret even third-party models, supports the analytical workflow during model process and post-deployment. So this is during when we are building the model versus also when we have actually deployed the model. So with that, let me introduce you guys to Scalar. It's our humble step towards providing an intuitive library to understand analytical results much better. This is also building on the aspect of human in the loop, so that we could demystify the inner workings of a black box model. It uses a number of techniques for interpretation to identify the relationship between the input features and human interpretable decision boundaries that it could learn. And as I was mentioning earlier, it could interpret models both before it is deployed and after it is deployed. So Scalar, it uses, it's model agnostic because we want it to work against different models. And we also have, it supports global and local interpretation. So for global interpretation, it makes use of feature importance, comparing independent input variables importance with respect to the predictive value that it's trying to learn on. It uses partial dependence plot for global interpretation again. This is a visualization technique. It could be one-way interaction or two-way interaction. One-way interaction is just a fancy way of saying that I have my predictive variable y and a variable a, and so it's a univariate interaction that I want to understand. If it's a two-way interaction, it's again a sophisticated way of saying that I want to look at 3D plots because I want to visualize at least two features with how my predictive value is interacting. More than 3, humans struggle, so that's why we don't have it yet. Then there's the aspect of local interpretation. I also have a small quiz towards the end, and I have a surprise gift for whoever gives the right answer. But so for local interpretation, Scalar uses a novel technique called LIME. It's the work done by Professor Samir, Marco, and Professor Carlos at University of Washington. And this is it's a very awesome step in the right direction, I feel. So it uses that for local interpretation. So in this example, what we have done is, what we have done is, we have taken two third-party models. And these are both deployed models. One is Indico and Algorithmia. Are we familiar with these APIs? No? So the story is that I had to build I was doing a topic mining analysis where I had to not only identify customer reviews which were positive or negative, sentiment analysis, but I had to also identify if a person is happy, why is he happy? If a person is sad, why is he sad? So it becomes very important for me to understand what text or words were actually contributing to it. And I was in a big dilemma there, whether to build the whole sentiment analysis model myself, or do I use a third-party model from some REST API for some provider. And so, that's part of the decision as well as to why we went down the path of building Skater. So in this example, this is an IMDb review for House of Cards. As you can see, it's a positive sentiment. But now being able to compare two models head to head, I have an understanding that, maybe the Indico model is doing much better, but it has learned on a lot of stop words, as you can see with respect to and is, where the Indico model is focusing more on the words which should be strongly associated with positive sentiment like good and ability. So maybe if I test more, I might realize that the Indico model is not as general as I thought it would be. What about images? So Skater also uses Lime for image interpretability, but this is experimental. We are still exploring better ways to do it. So in this case, it's a cat image. Can we highlight the feature boundaries which are actually contributing to this image being classified as cat? If it's a dog, can we do the same? Any questions? So this blue boundary that we see, the yellow boundary is the one which the model actually learned on. Yeah, within the boundary. So this is the part. So for example, in this case, it did a good job with the cat, but the same model didn't do a good job with the dog thing. It didn't learn. So it's most likely if I use it to predict, if I continue the experiments, I won't be surprised if it starts making a lot of error with the dog images and starts classifying it as cats or something else. So to summarize, life without Skater is we are looking at black boxes, and Skater's objective is to enable model interpretability for experts and non-experts. With Skater, the objective is that can we support an intuitive library or provide an intuitive API with the help of which we can not only explore the models at the global level using partial dependent plots and variable importance, but also at the local level using novel techniques like Lime. And there are other experimental work that's going on, and there is more to come. So let's see how all of this fits together in the workflow. So let's see. So for how many of you guys is this workflow new? I'm guessing everybody's familiar with the workflow, right? So before we get into the blue boxes, I can reiterate. So we define an hypothesis for any problem that we want to solve. We handle the data, that we handle missing data, we do some data partitioning, some transformation. Then we start getting into the phase of doing feature engineering and selection. We select relevant features, we build a model. We have done a great job, we check on the test and validation set, we get 90% accuracy, hooray. Now, if we are solving a real problem, we may have experimented with multiple models, and then I might want to explore. So then is the aspect of model interpretation. Can it help with model assessment, explain the models again at the global and local level? Also, can it help in generating insights which I could share with my colleagues and my superiors so that I could get the go-ahead or the green signal to go and deploy the model? One goes ahead and deploys a model, it's into production, then there is the aspect of testing, model testing and monitoring, model experimentations like A/B testing, multi-arm bandit testing, and so on. Then again, as the data is changing. I want to understand what that the variability in that data is that is contributing to my model variability. And again, there is a need for model interpretation. So that is explore and explain the model behavior once it is deployed, provide capabilities to debug and discover errors to improve the performance. Right. So I would say that's very use case dependent. Like for example, so I can give this example. So like when I was doing matchmaking, so we had multiple different models. Some models it was okay for it to be trained within 24 hours. For some models it was important for it to be trained every 1 hour. Because it's just what use cases one trying to solve. Like I can give an example. So if one has to predict the choice of restaurant based on the location that you are in. So as the location is changing every 5 minutes, you may want a different prediction. So at that point in time, if the model doesn't have a good generic understanding of the user's behavior, then it may start giving you choices which you don't like, and which we all experience when we use a lot of these apps. It's like starts predicting food choices. It's like, I don't know why it even suggested me that. Netflix, if you guys would have observed, recently they've changed the UI, and you could see the percentage, it displays a percentage of similarity. So it's say 90% match or 92% match. This is again a step towards enabling transparency as to why it is suggesting this movie. So we could understand how it has learned our viewing patterns. So we talked about model interpretation. So how do we do it, especially in an enterprise setting? So on that, let me introduce you to our datascience.com platform. Some of the things which I really like about our platform is convenient resource allocation or selection. So typically when we are doing, so this model building or predictive modeling is an experimental science, which means we are not sure about a resource. We don't know where to start. So it's often we may select a small resource, and if the result is good, we may want to scale. So having the ability or convenience in selecting the resource makes it very easy to continue the experimentation. So one other problem that we are facing in the industry is with respect to best practices, right? We want all our experimentation to be reproducible. So for reproducibility, can we borrow some of the well-established engineering paradigms that has been there in the software industry for a long time? That is version control. So our platform provides multiple choices for selecting the version control repository. Then the last one, the choice of kernel. This is where Jupyter starts shining again. Within one kernel, one gets the choice of selecting multiple different kernels. Within one Jupyter session, one gets the option of selecting multiple different kernels. That's very convenient. Our platform also supports interactive deploy, which is a convenient way of deploying the models into production. The whole objective is that we don't want the experimentation that is done on a platform to just sit idle. We want the work that all of us are doing to get out, to see any experimentation that is being done, it should see a day of light. Then only we have seen success. Either it is contributing to the business decisions that are being made, or it is contributing to the success of a product. And so that's what I've tried to show here is, and then again, going back to the aspect of reproducibility, that's very important. So all deployed models are tracked, they're version controlled. As you can see on here, we keep track of multiple different models that get deployed for a particular model. So with that, let me show you a scooter demo. So I might need a little help there because oh, cool. For some reason, when I was checking my presentation, the demo was not loading. So this is how our platform looks like. So it's about starting the project in an organized way. So we start with the concept of project, establishing native integration with version control. So in this case, this is a model interpretation guideline project. One could easily launch a session. being short in time, I'll skip the steps, but more than you guys are all welcome to check out our booth if you guys have not already. We have very exciting demos there. So let's get back to Skater using Jupyter. So in this case, what I've done is I've used the popular common breast cancer Wisconsin data set. And what I've built is an ensemble model, which is a collection of multiple different models. And the objective is that, can I use Skater to discover what's going on? Can I even do that? So we have an understanding, right? So the reason we also mentioned about model agnostic, life would have been very easier if all these different frameworks would just enable the coefficients that the model is learning on right off the bat, right? So if we get the coefficients from any neural network model that we have built, maybe we can learn the interactions across individual layers. That may not be enough, but if all frameworks are doing it in a consistent way, life is still much easier. But that's not the case. That's the reality of it. So that's the reason why it's important to do it in a model agnostic way. So here I've loaded the breast cancer data set. I forget how many features it has. Maybe it is mentioned somewhere here. So there are 569 rows and there are 30 features. Cool. So we loaded the data set. Can you guys all see the screen well? So in this example, to create the ensemble, what I've built is I've taken a linear model, a random forest, a naive-based classifier, and I've combined them, and an ensemble model as well, and I've combined them all together using a voting classifier, which is, so I've taken 3 models here, that is logistic regression, random forest, and Gaussian naive-based, and I've combined them all together using the voting classifier. Now can I do model comparison? Remember we said that why do we need? Now being able to compare how my features are just with respect to the feature importance. How are my features changing with respect to different models? So as you can see, linear regression, worst area is very important. That's still the same. But something changed when we actually combined all the 3 models together. In this case, it's still the same with respect to ensemble, but with random forest, things change because now in that case it's the worst perimeter. So even with just this basic understanding of feature importance, we have discovered that something different is going on with respect to random forest. So now what we did is we did a simple model comparison. If we look at the score, we can see that random forest has given the best accuracy on the static test data set that I had. One, is 100% accurate, while the others, the ensemble, is giving 97% accuracy. So now let's see if we can play with the model to dig deeper. This is the aspect of human coming into picture, right? So I've used Jupyter or IPython's widget API to create this, the aspect of including human in the loop. So now let's change the gradient a little bit and say we select perimeter and worst area. Then I had a button here, that's what I'm looking for. Do you see any button? I'm not sure where did my button go. But the idea here is that one could use the widgets and keep changing the perimeter, the feature space here, and could look at the one-way and two-way interaction. So in this example, what I've shown here is studying one-way interaction with the predictive value. So it's worst area and then mean perimeter, because those were the 2 ones which I had selected. Now, using the Skater library, one could also generate two-way interactions, which we can see here. Then going quickly to the local interpretation. So in this case, I've used again a simple slider using Jupyter widget, and as I can change the slider, it will generate local interpretation. So now you can see that for individual predictive rows, I can look into what were the top features and what were the contribution to the actual prediction, right? So moving ahead, a little short in time. So some of the experiments that we're doing for future is that all this is good, but we as humans are very comfortable in understanding if and else statements, because when we reason, we also think like that, right? If this happens, maybe we could do that. If that happens, maybe we can do this. So can we build models like that? One, it will help in better collaboration, very clear and transparent decision, understanding of decision boundaries. Now, with respect to images and text, things gets a little more tricky, but the objective is, can we have the images as well? Can we identify what are the areas in the image that is contributing to a particular decision? So like in this example, it's a dining room. What are the features and what is the probability scores associated with it, based on which it predicted that it's a dining room? If it's a bathroom, similarly, what are those image areas? So we have, like I was mentioning, we have lots of exciting work which is coming soon. But at the same time, we can't do all of this alone. We need help. Feel free to check out our library on GitHub. If you just search for GitHub and Skater, it should pop up. We've been trying to articulate or going, filtering through our list of action items that we have to complete and tagging it clearly, so that we could take help from the community and encourage everyone to come and participate in this journey that we have started working on. So with that, I'm open for Q&A. I think we have like a couple of minutes. Questions, yeah. Oh, sure.
Right now, if you were to run a linear regression model, we can isolate the impact of each of the features using coefficients. Does Skater afford any of that ability, even on an individual layer basis?
So Skater right now doesn't have the ability to understand in between layer interactions, but that's something we are looking into. But the most important thing is, at the end of the day, we have input coming in, and even if we understand what the interactions of those inputs towards the end, like the final output, irrespective of the 100 layers that we have built, what is the average weight towards the end? If we could capture that in a coherent way, that would be a great help. So right now, Skater, if one wants to evaluate a neural model, they can do that. With, again, going back to feature importance, so you build a neural network model, you run it against Skater, you can compare or evaluate the feature importance, and then understand feature interaction with partial dependence.
Yeah, I understand. You can get the feature importance, but I'm trying to see if you can isolate the contribution of each of the drivers or features that contribute towards your predicted value. Is that something Skater can do? Because I know that there are tools that SAS has, for instance. If you use Jump, there's a tool called Profiler, which enables you to do that at the moment.
Right.
Does Skater have something similar to that?
Not right now. But would be interesting to know if what your thoughts are and how we can add that. One thing that we're thinking of is like how to have or enable better interaction or understanding interactions in between layers, and then towards the end as well. So that's one thing we are thinking and evaluating how to effectively capture that.
DARPA had a paper about explainable artificial intelligence. If you know it.
So I've been reading so many papers. I think I might know the paper about which you are mentioning. So the question was, what are my thoughts on that? So I feel very positive about the space. I feel that in the next couple of years, the industry, we might see a lot of push by the industry. I mean, there's already a push in the, with respect to the research aspect of it, but we might see in the push in the industry as well to transparency of this, understanding the transparency and biasness of these algorithms that we are using every day. And just recently, Peter Norvig had come out, and he had also mentioned that, like, it's very important to not only understand this decision boundaries or the coefficients in the model's perspective, which is an expert can do that, but it's also it's very important to understand it in a human interpretable way. But then also he also had a caution that we as humans, we also disagree when we converse. So there will always be, I feel that there will always be an aspect of human in the loop, where we'll have to kind of have a control on the, like, the understanding, a control on our predictive model basically.